In this video, we're going to discuss parts per million as a concentration unit. So we've seen things like weight to volume and volume to volume, but there's also weight to weight. This rarely comes up as a percentage though. The majority of the time when you compare weight to weight ratios, they're done in terms of parts per million. So a ppm is generally referenced as the mass of the solute over the mass of the sample. It's not really a solution because it's solid, and so same idea, but in solid state. Except that this, being that it's out of million, is times 1 million. 10 to the 6th is a million. How this will work out, if you had something like 50 milligrams of DDT in a 1.9 kilogram bird. So DDT was a pesticide. It was actually an extremely effective pesticide. So much so that we used it everywhere right away. It was super cheap, didn't seem to affect other creatures, wiped out pest insects on crops. It got in and interfered with some of the exoskeleton construction, and so prevented insects from being able to grow properly. Unfortunately, it also happened to interfere in calcium depositing of shells. So bird eggs would be laid with very thin shells which would burst when their birds tried to sit on them, and whole years' hatchlings were lost. This happened again and again. And with a bird species that might only breed for a couple years, losing multiple years of breeding basically wiped out the species. In one of the fastest turnarounds, we banned DDT all over. In fact, we don't even let other countries use it if they want support from the US. So DDT is almost used nowhere, despite that if used properly, it's actually very effective at keeping malaria and things down. Little spritz in a standing pond doesn't really get into the bird population. It's not enough like it was for agriculture, but it does stop local mosquitoes. And so, unfortunately, the loss of DDT is, as all things, quite a mixed bag. Many bad things happened, but there were some good things that are now prevented. We still test for it, though. One of the problems is it still gets in the bird systems, a few places we use it. And so in this case, we need to study how much DDT was found in this bird. Well, this is where parts per million comes in. We tend to use it for trace amounts of pollutants. Things that you don't need very much of. To reference this, though, my mass of my solute, my DDT, and my mass of my sample need to be in the same unit. I can't use milligrams of one and kilograms of another, so we can convert these to whatever mass unit we want. They just need to be the same. Well, 50 milligrams, there's 1,000 milligrams per gram, so move the decimal 3 times to get to grams. And then for kilogram, if we make it grams, well, those are 1,000 per kilogram. So we'll move 3 times, and what we find is that's 1,900 grams of bird. That times 10 to the 6th. So 0.05 divided by 1,900 times 10 to the 6th is going to be 26. The trace elements of DDT in this bird was 26 parts per million. And so there are 26 parts per million DDT in our sample. Whether this is a lot or little depends on what pollutant you're looking at. There are very different parts per million for different metals in drinking water, where we consider it safe. There's very different parts per million for chloralkanes and things. Whatever the contaminant is, there's a safe-ish number that we say is acceptable, and it's unique to every compound. A big part of that is it's not really telling us how much, not in terms of moles. It's telling us mass. So things that have the same parts per million can have wildly different amounts. Let's take a moment and think about a 100 part per million arsenic versus 100 parts per million sodium. At first glance, well, they're both 100 parts per million. They're both 100 out of a million. But that's 100 grams out of a million grams. In fact, we can simply write that as the case. If it's 100 parts per million, it is 100 of that thing out of 1 million of the sample. And so there's 100 grams of arsenic in every 1 million grams of our sample. And same here for the sodium. It would be 100 grams of sodium for every million grams of our sample. Well, let's say I actually only had 1,000 grams of sample. And so I know my solution is 100 parts per million. I have found what that ratio will look like. But if we actually use a kilogram, so 1,000 grams of sample to find grams of our chemical. That's going to be 1,000 gram sample. There's a million sample. Has 100 grams of arsenic, and so it'll be 0.1 grams of arsenic. And we'll find the same thing for the sodium, because it's 100 grams in a million grams. So if we had 1,000 grams of the sample, likewise we'd have 0.1 grams of sodium. For the same parts per million, you get the same weight, because that's what it's actually telling us. But if you try to convert these to moles, so find moles, well, arsenic is 74.92 grams in 1 mole for arsenic, and sodium is 22.99 grams in 1 mole. It's going to give us 0.0013 mole of arsenic, and it's going to give us 0.0044 mole of sodium. For the same parts per million, we actually have wildly different numbers of moles of those atoms. Parts per million, the reason you can have such wildly different numbers for different chemicals, you might actually be just as toxic. But because different chemicals weigh different amounts, you'd need a different parts per million number to tell the same number of those chemicals. Generally, it's a lot easier just to weigh something, which is why we use parts per million. So you can weigh your toxin, you can weigh the sample it came from, you can say whether that was a dangerous level, and then just use that parts per million as your reference amount. This is where we generally see parts per million used to describe trace amounts of a chemical inside our samples. Usually for pollutants is where we tend to see it, but if you're in mining, you might find it for gold. How many parts per million of gold are in this rock that you want to mine? It is also used to measure trace elements for things we do want. There's just a lot more times it's used for things we don't want.